So the best way to do this, you remember, we said you draw your table. Always you have your inputs P and Q. What else are we going to need? We will need a node P. So node P will be right here. And also we will need node P or Q. Node P or Q. Now we will need this column implying a node Q. So we will require also a node Q. The order doesn't matter. Okay, so now but the final column should be the overall thing. Node P or Q implying a node Q. Okay, so the final column will contain the overall statement. Okay, so the combinations of these inputs, you remember we said we should have a true, true, false, false, and then this one alternates true, false, true, false. Not P, not is just an inversion, right? You invert whatever you have. If it's a true, becomes a false. If it's a false, becomes a true. So not P becomes false, false, true, true. We are opposing these P values. Okay? Not P or Q. Not P or Q. So we are saying false or true. It's true. You must know these things, guys. Okay? I'm assuming that you still have a knowledge of this. Then false implies false or false is true. Yeah? Is this correct? No. Huh? False or false. It's like it's a switch. True or false. Or X as an addition, plus. False or true is true, that's fine. False or false should be false. True or true is true. True or false is true. Okay. Then in not Q, we are kind of inverting whatever input is on Q. So true becomes false. False here becomes true. True becomes false. And false becomes true. Now, finally, we need an implication. A true implies a false. Remember, in one direction, a true statement cannot be false. So this is false. But a false statement can be true. And true implies false is false. True implies true, that's automatically true. So we look at the final output that we are having here. So the output is mixed. If they were all, if the overall outcome was true for all, then it was going to be a tautology, because the statement would be true always. Then if it was false for every type of input that we have, then we call it a contradiction. So in this case, there is a mix of false and truths. So therefore, we would conclude and say the compound statement is not a tautology. Why? Its truth value or its truth values do not contain truths only. And it can be a contradiction as well because of there are truths in there. So, okay, so it's not a tautology because the outcomes are not overall T's. Okay, if all were all T's, then we are going to say, okay, then that's a tautology. I hope you understood. Let's move on to question number 4. Remember, the exam has about 10 questions. And you have to be very, very fast and accurate. Because I've seen a lot of students struggling to complete the exam in 3 hours. Because there are 10 questions in there. And look at this, we are still on question number 4. We still have 6 more questions to go. So now we are taking a little bit longer to do these questions because I'm trying to explain and we are writing the same. But in a typical exam situation, you should fly. And you have to minimize mistakes. You have to be very, very careful and you should be very, very fast. Okay? Consider the following conditional proposition. If xy is equal to 0, then x is equal to 0 or y equal to 0. Write, number 1, its contraposition. Alright? So the contraposition, it kind of opposes everything that is there. Alright? So it reads, if, so the contraposition is we oppose from the implication. We oppose the implication first. So we start with if x is not equal to 0, the one that is implied by the statement, we start with it in the contraposition. If x is not equal to 0 and y is not equal to 0, we oppose, then xy is not equal to 0. Okay? So secondly, its negation. The negation of a statement only opposes the implication part. Okay, so if xy is equal to 0, the word then changes that to and x is not equal to 0. We negate that, and the word or changes to and y not equal to 0. If x and y is equal to 0 and x is not equal to 0 and y not equal to 0, so that will be the negation of that statement. We only negate the implication, the front part, from the comma going forth, we negate that. Remember, words like then change to and, the word or changes to and as well. Okay? Alright? So let's try use by proof of contrapositive. Remember, the contra of any given statement, if you can prove the contra of any given statement, then that statement, if the contra is true, then the statement is true. I'm sure you remember we did quite a number of these examples before. So use proof by contrapositive to show that if n squared is an even integer, then n is an even integer. So we start off by saying by contrapositive, we need to write down the statement in contrapositive form. So we say assume n is, we start from here, the implication. Assume n is an even, so we say n is an odd integer. That is, what does that mean? If n is an odd integer, it means n is equal to 2k plus 1 for some k element of integer. For some integer k, then the contra is that we are assuming that n is odd. Then it means n squared is odd. Okay? Then n squared is equal to, okay, we should show that n squared is odd. That's the thing. So, but then n squared is equal to, we take our definition 2k plus 1 all squared. If you expand this squared bracket, you end up with 4k squared plus 4k plus 1, which can be written as, if I factor out a 2, I'll have 2k squared plus 2k plus 1. Now, if I let, so this is equal to 2m plus 1, where m is equal to 2k squared plus 2k. M is an integer. Alright? And clearly 2m plus 1, this is the structure of all odd numbers. So we say therefore n squared is odd. Okay? Thus, by the method, you have to conclude. If you don't conclude, you lose marks. By the method of proof by contrapositive, we conclude. In the conclusion, you write the statement as it is given. We conclude that if n squared is an even number, integer instead, then n is an even integer. Okay, full stop. I think that's clear enough. I'll give you, a PDF of these things so that you can use them for your revision. All right? You have to go through these questions alone and try to reproduce the solutions that we are discussing now. Okay, are you still there, guys?
Yes.
Okay, perfect. Let's move on to question D. Prove that root 3 is irrational. In other words, prove that we cannot write root 3 as a fraction a over b, where a and b are integers in their lowest terms without a common divisor. That's the idea. So you start off by saying, so you can't do a direct proof for this one. Rather, you prove by contradiction. All right? You say, assume that root 3 is rational. We are kind of contradicting what is given. Then I'm saying root 3 can be written as a over b, where a, b are integers, b is non-zero, and both a and b, a and b are in their lowest terms. Okay, so therefore we are saying root 3 can be written as a over b. What do? We square both sides. We end up with 3 equal to a squared over b squared, and you can see that a squared is equal to 3b squared. What does this mean? It means that which means that a squared is divisible by 3, and since a squared is divisible by 3, and so is a, okay, if a squared is divisible by 3, then a is also divisible by 3. So a is equal to some 3m, because a is a factor of 3. Thus, okay, or we can just say, which implies that we can replace a squared with this 3m, so it becomes 3m all squared equal to 3b squared. So 9m squared equal to 3b squared, and you can see that b squared is equal to 3m squared, which means, again, that b squared is divisible by 3, and so is b. Now, hence 3 divides, according to our proof, 3 divides both a and b, and this is, or we can just remove this end because there is ambiguous there, ambiguity. So say this is a contradiction of our assumption that a and b have no common factors. So root 3 has to be irrational. It seems to be, too much wording, but this wording is very, very necessary in the proof. Very, very necessary. You can't omit this wording because it links up your proof. You must train yourself to write these reasonings, okay? So now that we have done for root 3, you can try do for, say, root 2, okay, for practice purposes, even root 5. Prove that these are irrational. Okay? I'll leave that as homework. But it kind of follows the same pattern. I'm sure you'll be able to do that. Alright, so let's see. Let's move on to question D. Use the method of mathematical induction to prove that for all n element of n, this formula is true on all natural numbers. Natural numbers are counting numbers, 1 up to infinity, right? Positives, whole numbers, 1, 2, 3, 4, and so on and so on. So in order for us to prove this, you remember when we were doing the revision, I told you that you should say let Pn be such that we need a Pn, the Pn statement, because we will always be referring to it from I equal to 1. Pn is just the thing that you are given as it is, okay? The entire thing. So summation of 3 to the power I equal to 3 over 2 into 3 to the power of n minus 1. This is your Pn. You can just add for all n element of natural numbers. This is our Pn statement. Then we need, it has steps. The proof by induction has steps. So we need a P1. P1 is such that where there is n, I'm going to plug a 1. So the left hand side, as you can see, the left hand side of this formula is two sides, this left hand side and the right hand side. So if I plug where there's n, I'm going to put 1. So I'll have summation from I equal to 1 up to 1 of 3 to the power I, which will be just 3 to the power of 1, which is just 3, right? And let's do the right hand side. The right hand side will be 3 over 2, 3 to the power of 1 minus 1. So 3 minus 1 is a 2, so that's 3 over 2 by 2, which is equal to 3. And this 3 is just the same as the left hand side. Hence, P1 is true. So the formula is true for n equal to 1. The second step is to assume that is true. So we assume that Pk is also true. That is summation, where there is n, we are replacing with k. So summation from I equal to 1 up to k of 3 to the power I is equal to 3 over 2, 3 to the k minus 1 for some k element of natural numbers. For some integer k. Okay, it's fine. And then it's just, okay, we can just use positive integers. Okay, it's just the same thing. It's one and the same thing. You can just have it as integers there or natural numbers. That's okay. Okay, so now then we must prove that it is also true for Pk plus 1. That is, let me insert some space there. Insert space. That is summation, we need to prove this, from I equal to 1 up to k plus 1 of 3 to the I is equal to 3 over 2, 3 to the power of k plus 1 minus 1. So we come down here and write down the proof. So when we are proving, we start off with the left hand side. So the left hand side, summation from I equal to 1 up to k plus 1 of 3 to the power I is just the same as summation from I equal to 1 up to k of 3 to the I plus the last term would be just 3 to the power of k plus 1. Okay? If I add up to some k with the formula, then I don't need sum for the last term. The last term, I know it. I will just replace I with a k plus 1, which is just this last term. Why did I do this? I want to use for this part, I want to use the assumption step. That's why I did that. So then this is equal to, but according to the assumption step, this is known, right? I equal to 1 up to k is known to be this thing. So it will be 3 over 2. We just replacing with that, where I'm putting a star here. We're taking all that. So it will be 3 to the k minus 1 plus the 3k plus 1 comes back. Okay? So let's simplify further. This is equal to, now if I'm going to remove brackets, I'll end up with 3 over 2, okay, times 3 to the k minus 3 over 2 plus 3 to the k plus 1. Okay, I just removed brackets. Now if I group these things together, you will agree with me that if I factor out a half for the first part, if I factor out a half, there will be 3 times 3 to the k. So if I factor out, so I'm saying, what am I saying? I'm saying 3 over 2 times 3 to the k is just the same as half out 3 times 3 to the k, which is just half out times 3 to the power of k plus 1. This is exactly what I want to do. So I will have half times 3 to the k plus 1 for this first part. Then I want to bring this 3k to the 3 to the k plus 1 closer. So it's a plus 3 to the k plus 1 closer. Then lastly, minus 3 over 2. Okay? Okay, until now we good. Okay, so then what do you think should be done? If you look at these, we want to kind of combine these things. If I split, look at this, let me take a different color. I'm trying to find, so look at this term that I'm circling. If I am going to, because why am I thinking this way? Look at the right hand side that we want to achieve. Let me pick a different color. This is the right hand side that we want to achieve. Okay? We have a 3 over 2 factored out. If I look at the expression now where I am, the 3 over 2 is fine. This one is okay. But here I don't have 3 over 2. So I must take a 3 from here and place it on top of this. I'm not quite sure if you are following. So if I take out okay, so I want to generate a 3 over 2 here. So, okay. Look at, there is a coefficient in front of this number. The coefficient is 1, but it's invisible. Okay? So there is a half of something plus 1 whole of something. So, if you combine 1 plus half, you will end up with a 3 over 2. Half plus 1 is 3 over 2 times 3 to the k plus 1. Then this negative 3 over 2 comes back. Then I can factor out 3 over 2 out into 3 to the k plus 1 minus 1, which is exactly what is appearing on the right hand side. Hence, proved. Then we need to conclude by the principle of mathematical induction, summation from I equal to 1 up to n of 3 to the I is equal to 3 over 2 into 3 to the n minus 1 for all n element of natural numbers. So this is how we conclude, guys.